Good afternoon, everyone, and welcome to our sixth seminar of this fall series of Sunoikisis's digital culture heritage. Today, we're talking about linked open data, and our guest speakers for today are some old and new friends. We have Paula Granados from the Open University, Matteo Romanello from the PFL Lausanne, and Gabriel Bodard, we all know very well, from the Institute of Classical Studies in London, where I'm also based. And I think that Gabi is the one that will be starting this conversation about linked open data.
Sure. Thank you, Valeria. So just briefly, to give you the outline of this session, I'm going to give a very brief user-focused introduction to what linked open data, where it comes from, and how it fits into the semantic web, etc. But then to go a bit more deeper into the theory, Matteo is going to come and talk us a little bit more, and also give some examples of content negotiation. He'll explain what that means. I'll then come back and this time be rolling up my sleeves and getting covered in engine dirt and showing you what the underlying technologies look like and explaining the concepts of RDF and ontologies. Then we'll have two case studies. The first by Paula on the cultural contact ontology, and the second by Matteo on the Hucit ontology. And finally, we'll have an introduction to Sparkle, the linked open data query language, which will lead us into the exercise, which will all be given by Paula again. So if I can start with my slides, please, Valeria. So I'm going to talk about the theory behind linked open data from the perspective of this the concept of 5-star linked open data, which I'll explain in a minute what that means. This is the most common categorization for what makes good linked open data. Just a very quick point about terminology. It is sometimes pointed out that the technical or perhaps slightly pedantic distinct difference between linked open data and linked open data is that when written with all the words capitalized, linked open data is this concept that we're talking about this week. We're talking about theory, ecosystem technologies, etc., around openly licensed structured data linked to other data. So that's linked open data, the concept. When it's written all in lowercase, then linked open data refers to a specific data set or a particular piece of data in some digital format. So say, here is some linked open data for you to look at, that you wouldn't capitalize. If we say we're talking about linked open data, that you would capitalize. No one is consistent about this, and we certainly haven't been, but that's the general idea. So when talking about linked open data, very often the first image that people will show will be something very similar to that, or sometimes it'll be something like this. The person who so-called invented the World Wide Web, but also came up with the concepts of linked open data. But if let's stick to the cup, you'll find very few linked open data geeks who don't have this mug on their desk. And this is the concept of 5-star linked open data. This gives you the 5 criteria that make your work qualify, your data qualify as linked open data. So I'll just go through these very quickly, and then I'll add a couple more stars at the end that come from other places. Just to explain the concepts a little bit. Again, not in a particularly technical way, but from the perspective of data and the web. So the first star is simply that the data has to be open. And by open, we mean it's under an open license. So you've taken your data, you've put it online somewhere, and you've said, with the license, that people can take this data and they can reuse it. Okay, and there's no other criteria to get the 1 star. Your data can be as simple as a screenshot of a table of data or whatever. It can be a photograph. It's just raw data in some form that is online and that people are free to reuse. You get the 2nd star if your data is structured data. That is to say, if instead of giving us a table that you have drawn on a napkin and then taken a photograph of, if instead you give us an Excel spreadsheet or some CSV or some any digital structured data, then you get the second star. This data is then much more useful because people can not just look at it and interpret it, but they can actually take it and reuse it in various ways. You get the third star for making it available in an open format. That is to say, not a proprietary format like Microsoft Excel or Google Spreadsheets or Apple Sheets or any other specific closed source software, but in an open format such as a open SQL database or a simple CSV comma separated values text file. So if it's open, that people can use it regardless of whether they have the software that you use to create it or not. You get the fourth star if the entities in your data have unique identifiers that enable people to point to them unambiguously. So not only identifiers that this is item number 17 in my data, but a unique identifier that is unique across the whole world. And we'll talk a little bit later about what we mean by unique identifiers and how they work. I think Matteo will talk about that in a minute. You get the fifth star if, in addition to having these URIs so that people can point to your data, you also point your data to other data. So the data that you have made available in these open formats and with identifiers in them is also linked to other data in similarly open and transparent formats, so that it begins to have this huge contextual network of data across the web. This then, once you have all 5 stars, this is linked open data. People have, this is broadly accepted as a description, but people have attempted to either dispute or perhaps supplement this definition, and I'm going to briefly just mention these 4 additional criteria that Weinsmith has added that he believes are necessary to make linked open data actually useful and usable, and these are that your data should be relevant to you, should be useful to you before you share it. Don't just dump everything you have out there, but specifically link that data which you are using and which is important for your internal use in your project, in your institution. And correlated to this, that you should be using your data, not just that it is potentially relevant data, but that you are specifically using it. You are using it to make your own inferences. You're using it internally. You're linking it to other data that within your project, and this is part of the research of your project. Linking data that you're not using yourself, according to this definition, is not particularly useful. I would actually dispute all of these, I think, but certainly this does make it that little bit more useful if the data is not just thrown out there, but it is also in use and internally. Thirdly, support this data with as much context and metadata as possible. So don't just say, this is the information we have about this pot, but what is the quality of this information? Where did it come from? What is the curatorial history of this information and data and so forth? That is of course very important for all data. And the final one is that you should specifically select and work with the community of users who you want to use your data and to preserve your data and to work with your data. And these users should be the very people who you have started by linking your data to in the 5th star in the traditional set of definitions. So this gives you a bit more of context of what makes linked data useful, as well as just what makes it linked data. So I'll stop there for the moment, just because I wanted to do that as a very broad context, and hand over to Matteo, and then I'll come back with a bit more technical stuff later.
Thanks, Gabi.
Over to Matteo, yes.
Sorry. Yeah, so let's go a bit deeper into the theory of linked open data, and also look at the content negotiation, and you will see in a moment what it is about. So I think to understand linked open data, as opposed to the web we are used to, we need to change a bit perspective. So the web we are used to browse as humans is a web made of documents that we look up in a browser. And typically we read it, we look at it, and we follow links to other documents. In the web of data, this is not how the content is consumed. So the web of data, you can think of it more as a web for machines, not really robots, but more for user agents. Instead of reading web pages, they consume bits of data. They still use URIs to get the resources, but they consume it in a different way. So we change a bit the perspective, and now we look at how does it look like, this web of data in the context of linked open data for machines. But before looking at the technical details, a bit of rationale. Why do we want to do linked open data, and why is it useful? Well, the main goal is to overcome information silos. So information on the web is published and scattered in many different resources. Here in this slide, you have just 3 about Homer. They all give complementary information about Homer. And it would be very nice to have all this information interoperable, talking to each other in a single place, consumable in a unique way, in a common way. Instead, we have 3 resources. So on Wikidata, you have lots of facts about Homer. In the Perseus catalog, you have bibliographic records and links to online editions and translations of Homer's works. And then in VIAF, you have an aggregation of metadata coming from the libraries, more with authority data, all kind of aggregated together. So it would be nice, instead of having 3 different ways of publishing this information on the web, to have a way that machine can consume the information, the data behind these resources, and actually use it all together, all these three things together. Probably the main ingredient of linked open data, as Gabi mentioned already, are URIs. So URI stands for Uniform Resource Identifier. They are a type of identifier. In linked open data, we are dealing with HTTP URI, which are a subclass of this URI. URI is just a string that we can use to unambiguously refer to a resource. And this resource could be a resource on the web, an email address, a telephone number, something else. That's why you have different subclasses of URIs depending on the namespace or the scheme that they are using. So HTTP URIs are those identifiers in the scheme HTTP, and the namespace is the domain of the web. They are different from URLs, from uniform resource locators, because a URI is not supposed to give you back necessarily a web page, whereas a URL does. So if you look up a URI on the browser, even if it's a valid URI, you might get a 404 because it doesn't correspond to a web page. So there is this difference to be kept in mind, and we'll also come back later. So let's look now a bit at the role of URIs in the specific context of linked open data. So we use them as a reliable, unique way of referring to entities. And entities could be persons, organizations, relations, fictional entities, and so on. How do we know that this uniqueness is guaranteed? Well, in a URI, you have a domain part which is going to be unique. So even if we use the same identifier to refer to things, if we embed it in a URI that has a different domain, then we still have a unique URI. So let's take as an example the case of a URN is a CTS URN for Homer. Even if we imagine 2 resources using the same identifier to describe 2 resources about Homer, the fact that they are using their own domain within the URI means these 2 URIs will be unique. Another property of URIs in linked open data is that they should be dereferenceable. What does that mean? Sounds a bit scary and technical, but you can think of it as going back to the robot and the human. The reference, a URI, is just the way that the machine reads a resource. So we as human, we look up something in the browser, the machine or a user agent is dereferencing a URI, but it's really kind of the same operation of reading, consuming a resource. And to exemplify what does it mean, this dereferencing, I will not do a demo, but just show you a nice little tool, which is called, it's a command line tool, which is called curl, which is basically mimicking the way the machine consumes a URI. So content negotiation is this mechanism of looking up URIs. Even if you have never heard of the term, you are using it all the time, because whenever you open a web page in your browser, what you're doing is to do a content negotiation. So your browser is looking up a URI, asking explicitly to have back some content in a given format. And the browser normally is asking to have HTML back. So with curl, you can do the same, but kind of mimicking the way a machine does. So what you do is to type curl, then with some parameters that I will explain in a second. But the most important one is this -h parameter, which is the HTTP header. And in the header of the request, we are saying, please give me back some HTML. So when we look up, for example, a Wikidata page, this is the Wikidata page for Homer in this way, then we get back the HTML. And this is how the browser is representing this URI if you open it up in the browser. So it's an interaction between a client and a server asking for some content in a specific format. In the context of a linked open data, we say that URIs should be dereferenceable and they should give back some information in one of the standard formats of linked open data. For example, RDF XML or JSON LT or Turtle, which are all different serialization formats of RDF. So if we want to mimic this negotiation, we just change the accept parameter in the header, and instead of asking for HTML, we can ask for RDF XML. And if you try this in the on your command line, you will see the same. You will see that the answer of the server is changing. Instead of receiving back HTML, you receive back RDF. And this is how content negotiation works. I think that is interesting to note for Wikipedia, for Wikidata in particular, is this -l parameter. So you can try to do the same command removing the -l, and the response will change, because -l tells the client to follow the redirect links. So the Wikidata links for Homer, it's actually when you ask for RDF, redirecting to another page, which is this page in the special entity data. So there is a redirect, and by using this -l parameter, you tell curl to follow these redirect links. And this is because Wikidata is using two different URIs to refer to two different things. So the first URI is to refer to the entity Homer, and the second URI is to refer to what Wikidata knows about Homer. And they have two separate URIs because they are two separate things, in fact. You can also try to break this system. If you pass as a parameter accept something that the server is not able to deliver, then you will get back an answer saying this format is not supported. And this you can try to see what formats are supported by Wikidata when you try to negotiate the content for its URIs. I wanted to mention before finishing this section two other things. One is the process of data reconciliation, which it's a common phase on when someone is producing linked open data. since linked open data, it's all about creating links to other data sets. An operation that we do very often is to take our own data set and trying to link it semi-automatically with other URIs coming from other data sets. And this operation, it's called data reconciliation. And I've posted here two links to two resources to do this data reconciliation using a tool which is called OpenRefine, where basically you can load your data set and trying to reconciliate with another resource. For example, one can try to reconciliate a data set against Pleiades, the gazetteer of place names, or against Wikidata. And in these two posts, then it's explained how this works. And finally, I wanted to finish with a shout out to a current project. I think there are many cool projects in digital classics about using linked open data as a methodology. But a very interesting one, which is still ongoing, is this Lila, linking Latin, which is using linked open data to link together linguistic annotations about linking text. So it's all this idea of using linked open data to break down, in this case, silos of linguistic annotations and enrich the data by doing so.
Okay, thank you, Matteo. And I think it's back to Gabi now.
Yes, thank you. Could you just pop my screen up, please, Valeria?
Sure.
Thank you. So I'm going to talk briefly now from a slightly more technical perspective of about RDF, which is the language, as Matteo just explained, in which linked open data is very often expressed, and also about ontologies, which are something which help us to find these URIs that we use in linked open data. So RDF is effectively, it defines a statement in the context of linked open data as the simplest possible sentence containing basically 3 words. So your sentence has a subject and a predicate and an object. All 3 of these may be URIs. The first 2, I think, more or less have to be URIs. The third one could be a URI or could be a string, and we'll see examples of that in a moment. But the URI that is the subject of your sentence will come either from an ontology or some other kind of vocabulary, or from a site like like Wikidata that Matteo's just talked about. The predicate URI will tend to come from an ontology. This is something that gives us the vocabulary of our language. This is a list of all the verbs that are available to us, if you like. And the object may be anything that can be used to describe or to relate to the subject in some way. So it could be another entity defined in a vocabulary or an ontology, or it could be an adjective of some kind explaining, giving some quality of the subject, or it could be a simple string describing the subject in some form. So I'll just give a couple of examples of these statements, and note that I'm not yet talking about the language in which we express these statements, but simply the syntax of them, the semantics of them. So a couple of examples here. The first is a simple sentence. Julius Caesar is, or was, but let's say is, because a simple triple doesn't have the concept of time built into it. So if something is true, it's always true. So Julius Caesar is a dictator. In this case, the simple sentence, which in English we expressed using these words, is expressed in RDF using these 3 URIs instead. So Julius Caesar, for this historical entity, we use his Wikipedia page because that's a fairly unique string that unambiguously refers to that person. That may not be the best thing you could use, but it's a perfectly acceptable thing to use. For the concept of is, we use this RDF ontology. It's that has this URI that is given here, and this is the single most common property in this ontology, which is the property type. So this is sometimes referred to as RDF type, and it is so common that in many RDF languages there is a shortcut for that, which is simply to say A. So Julius Caesar A dictator, because this RDF type is such a common thing. But this basically just means is what is the type of the subject of this triple? Well, the type is just given by the object, and the object is dictator. And for the concept dictator, rather than using a string, which is potentially ambiguous, because dictator in modern English means something slightly different than it did in 1st century BC Rome, where it was a technical political role, and may also have different connotations in different modern languages. We use the Wikidata URI, which specifically defines, I mean, it's not a Wikipedia page it is a linked data concept linking together various different pieces of information, specifically on the concept of the Roman concept of dictator. Okay, so that's one example of something expressed as an RDF triple. Another example is a triple here that this person who has an identifier, an ORCID identifier, has a name, and so we use the FOF ontology for the name, and their name is given just as a literal. In this case, it's a string. That's how you spell their name if you're writing in French. There may be other languages in which you may write it differently. Okay, so that's an example of an RDF triple with a string as its object rather than a URI. And a third example, just to bring this into something that we might actually use in this module. In fact, we probably had something very similar to this last week, where we would have the subject of this triple is a mention of the place Ithaca in a recogito file document, and that mention refers to, using this open annotation ontology that is used by Pelagios, and it refers to the Pleiades place 53905, which is, if you were to follow that link, the Pleiades entry for Ithaca. Okay, so that's another example of a triple. Having said, having just talked about how RDF expresses these things in very simple triples, Matteo has already said that there are various different ways of serializing RDF, and this triple format, this concept that each statement is made up of these three elements, can be expressed in many different more concrete languages. So you have RDF XML, and this is an example of RDF XML where we have various elements that have the information that is embedded in that RDF. So this is a fragment of RDF XML which makes two statements. It has two triples. One, it says, is that the webpage rdfschools.com, w3schools.com rather, has the title W3 Schools, and the second, which says the website w3schools.com, has the author Jan Egil Retsnes. So that's just a very simple piece of RDF in RDF XML. That's not XML in general, and RDF XML in particular, are not meant to be human readable. RDF is not really meant to be human readable anyway, but Turtle is a slightly more human readable. It's called terse triple language, so it's slightly easier for us to read because it basically puts things in order. So it'll say W3 Schools title, W3 Schools, W3 Schools author, etc. So it is slightly easier to read. A third format that Matteo's already mentioned as well, JSON LD, could express the same sort of triple information, but instead by embedding it in this very unhuman readable format, JSON, the JavaScript object notation. This contains exactly the same sorts of information that you would get in any other kind of RDF. Just this is very, very easy for many programming languages to get hold of very quickly and to process in various ways. This is becoming an increasingly popular way to express linked open data. And finally, you can express triples in a graph database, in any of many graph databases that exist, proprietary or open, that may not themselves necessarily be natively RDF, but that express and collect data in a very similar way to RDF and are very easy to generate RDF from as a result. Matteo's already talked about what URIs are. I just want to reiterate the fact that not all URIs, not even the HTTP URIs that we use in open data, will actually lead you to a web page. It's good if they do, but it's not technically broken if they don't. But if they do lead you to a web page, that web page may tell you more about the entity, or if you visit that web page specifically with a client that knows how to read RDF, it may instead give you RDF about that entity, which can further be queried. So where do these URIs come from? Just very quickly then, the URIs are defined in, as we say, in ontologies or vocabularies or other kinds of lists of things. So the Pleiades gazetteer has some tens or hundreds of thousands, I forget exactly how many, of places defined, and each of those gives us a URI for that place. So for the subject of our RDF triple, we might have people, and there are various collections of URIs for people, such as ORCID, which is an academic list of entities and people, VIAF, which is a library catalog aggregator, Wikipedia has a lot of people mentioned, and you can use their addresses, as we did with Julius Caesar, as URIs. The Lexicon of Greek Personal Names gives us a unique identifier for each person, each of the several 100,000 people in that database that can be used as subjects of RDF triples. Places, you'll have seen last week the geonames and Pleiades and Dare gazetteers, and there's also OpenStreetMap, which will give you potentially URIs for place entities within them. And various other sites will give you lists of URIs for texts, museum objects, concepts, web pages. Any web page could be the subject of a URI if what you're doing is describing that web page. There is sometimes a bit of ambiguity over whether, if the subject of my RDF triple is a Pleiades web page, am I describing Ithaca, or am I describing the Pleiades web page about Ithaca? There are various ways of addressing that ambiguity, but it's worth pointing out that the ambiguity is there to start with. The predicates, then, the second of our three words in our simple RDF sentences, are in some ways the most interesting. There's all sorts of different ontologies that give us ways to write triples that describe things. We've talked about the RDF schema already, doubling core, the linked ancient world data ontology, the Eagle ontology, all give us ways to say things about objects, about people, about places, about web pages, about documents. Relationships between people can be expressed using the standards for networking ancient prosopographies ontology, the FOF ontology, friend of a friend, that we've already talked about, and a couple of others, PIMO and SORS, which are, SORS is more about relationships between texts. Spatial information, Pleiades, GeoWant, and Topo all give us ways to say, this place is within this country, this city is the capital of somewhere, this city was destroyed in year X, these sorts of things. Time expressions can be expressed using various ontologies that I've listed here. And the objects can be any kinds of entities that can also be subjects, because we can say, person A has a relationship with person B. They can also be properties of various kinds. Properties can be thought of, if you like, in a sense, a bit like adjectives. So the RDF triple could be saying, this city is big, or this person is a general, or whatever. And there are various ontologies that express properties in specific ways. Wikidata has a lot of properties involved in it. The Getty Art and Architecture Thesaurus will talk about properties of material objects in various ways, and the objects can, as we said, be also be literals, which means they're just a text string and they're not expressed using a URI. Although it's worth noting that there are ways to embed URIs alongside the literal that give us more information about it, that tell us how to interpret that literal. For example, to say that this literal is a date, so you should read it differently than you would if it were a string or some other kind of number. So here's a simple example of an RDF triple. This one is expressed using Turtle, the slightly easier to read serialization of RDF. And this is simply saying that this first URL, which, because it begins example.com, you know doesn't really exist, doesn't really take you anywhere, but in an imaginary database of objects, pot number 17 is, remember this this second URL means RDF type, which is another way of saying is, and then the third URL is, if you follow it into the British Museum's thesaurus, it tells us that this is a particular type of pot, and I forget exactly which one it is, but let's say it was a lekithos. That is the entry in their thesaurus for the lekithos. And so it is saying that my pot number 17 is a lekithos, just using that simple RDF triple. Now, the one weakness of a simple triple like this is that to make academic statements, we need to say a little bit more. If I write an article and all I say is, this series of facts are true, that's not enough, right? That article also needs an author, and it needs some supporting information, and ideally, in order to be able to cite it in a bibliography, it needs a date. So here's what we do about qualifying that sort of information, or one of the approaches to qualifying that sort of information, is to, again using this open annotation scheme that Pelagios uses, is to, instead of having a triple simply being the subject, predicate and object, being the entities that you're describing in the first place, you create a new subject, which is the annotation itself. And then that annotation has several properties, one of which is its target, the thing that you're describing, another of which is its body, the annotation on that thing that you're describing, another might be its annotator, in this case it's a URI for who made the annotation, and another one might be the date and time at which the annotation was made, etc. And there can be other things attached to that. So then you can give all the qualifications that you would academically want to give on your statement of fact. This piece of RDF, which looks a little bit complicated, note that Turtle, because it's terse, it allows you to make several statements about the same subject. So here we've got the one subject, example.com annotation 1, and we have 1, 2, 3, 4, 5 properties on that subject, 5 triples, and the subject is only given once, just to keep it simple. You could repeat the subject each time; it would just make the whole thing slightly harder to read. But the semicolons at the end of each line, you see, are basically the word "and." So this URI refers to an annotation, type annotation, and it has target, and it has body, and it was annotated by, and it was annotated at. Okay, so it's making all these statements all at once. What this piece of RDF is actually doing is it's saying that here in this piece of text, this inscriptions of Aphrodisias 12614 that was referred to in the URI there under has target, that's where you stick the sticky note. It has a body, which is this snap person, and that the snap URI for that is that for the Emperor Vespasian, and the other information would be, if you like, a signature on the side of that, signature and date on the side of that post-it note. So this is creating an annotation, telling us where to put the annotation, what to put in the annotation, and then other information to attach to it. So there's just a couple of examples of RDF from a technical point of view. I think this will become much clearer when we look at the 2 case studies which are coming up now. So we'll hand back to Matteo, I think. No, to Paula.
I think it should be Paula. Yeah.
Hello, thank you very much, Gabby. I'm very happy to be here. And yeah, so my first mission today is to give a short overview about the cultural contact ontology. And Valeria, can you show my screen? Yes. Okay. So to start, I'm gonna speak about a little bit about the rationale behind the ontology. And the cultural contact ontology emerges from the research question that I pose in my PhD research. And my background is archaeology. And I was interested in seeing how linked open data technologies can help us in understanding the dynamics of cultural interaction in early Roman Spain. I specialized in early Roman Spain during my degree, and I had that chronological and geographical scope for my research. And so, as you know by Gabby's explanation, semantic technologies allow computers to understand the relationships between objects, normally in relation to place, time, events, and even people. But in order to understand cultural interaction and how linked open data can help us in perceive cultural influences in the objects, I started to wonder whether it was possible to look at the connection between objects based on cultural influences. However, the idea of a network of interconnected objects in relation to shared cultural influences is not new. This idea was already posed by Alfred Jell in a book he wrote in 1998 that it was called Art and Agency. In this book, Jell considered that all objects belong to one same network of materiality in which each of the elements is an instance. And this image that I'm showing is a very interesting example that Jell uses to reinforce his hypothesis based on the research made by Nage, in one of the houses of the Polynesia, of a Maori community of North Island. These researchers went there between 1550 and 1930, and he started to observe that some of the houses, which are represented here in the graph by numbers, shared very similar painting patterns. And so in this diagram that we are seeing, he represented how the houses are interconnected depending on the paintings they share. So Cuckoo, or the cultural contact ontology, borrows this idea of connecting objects based on the cultural influences that they share, in order to see whether we can understand better how cultural interaction happened in antiquity. And so, first, in order to understand how the ontology works, I wanted to show you some examples of how the type of objects that I am working with and how the data has been collected. So, for example, this is a coin in which we can see different elements such as the iconography of the reverse and the obverse, the legend, the reverse legend, which is it's believed to be Libyo-Phoenician writing, the obverse legend, which is probably a Punic name written in Latin, the iconography of the reverse, and the material. So all this data that I collected from the objects has been manually collected in the form of tabular data, and I needed a system to be able to model it, to model all these little bits of information from each of the objects. This is another example, which is a sculpture from the south of Spain as well, from Cordoba. And as you can see, we can see that it's made in limestone, and that it is a votive offering. It was offered in a sanctuary. We can see how the manufacture is very it's been identified with indigenous influence, and we can see as well that on the top of the forehead there is an inscription which reads Dea Caelestis. So we have a votive offering in a very indigenous fashion, but with an inscription in Latin on the forehead. So these two objects are examples of cultural interaction, because they present different sort of writings, different sort of iconographical influences. So in order to be able to model all this information, I started to review what was already there and what sort of models could I use. I discovered the EDH ontology for epigraphic data, the Nomisma ontology that deals with coins and mints, also the Eagle and the CDOC CRM as well, and the Pleiades vocabularies that I use to model information about data. Nevertheless, I couldn't find any ontology that was available in order to talk about culture, or in order to model cultural influences and cultural interaction. So in that sense is when, at that time is when I had to start thinking about developing my own ontology to model cultural interaction and cultural processes. And this is the sort of flow that the process flow that I follow. It is very important to stress that Cuckoo emerges directly from the necessity to model the data. So its development is directly linked to the data necessities and to the sort of examples that I came up with while studying the material record of the province that I was looking at. So as you can see, first, the first step is the data integration, to start thinking about the translation of tabular data into semantic data, into linked open data. Second, the concept identification. Once I had the data into a table, I started to think what sort of main concepts I would need to speak about, for example, cultural influences, cultural trait, cultural phenomena, and so on. Then concept-oriented research, which focuses on the evaluation of relevant sources for the concept definition. So I had to do some research on what types of sources could help me to better understand the sort of ideas that I wanted to model in my ontology. So I had to rely on other disciplines such as ethnical studies, anthropology, and archaeology as well, of course. And finally, the concept definition. After following these three steps, the final step involved the final definition of the concept on the basis always of the evidence that I was looking at from the beginning. And so, very briefly, I don't know if you can see it well, but this is a diagram of the classes, the main classes that I model in Cuckoo. As I said from the beginning, I was just interested in modeling the classes that could help me understand the evidence. So I didn't want to create this perfect model for cultural interaction. I just wanted something that worked for me to understand better my evidence and to be able to share it as linked open data. So as you can see here, the main core class is thing, because I use OWL as the language of Cuckoo, and in OWL the core class is always thing, and from thing other four classes emerge. The cultural agent on the top left. This is it emerges from Yale theory again, because for him he bases his theory in the concept of social agents, which can be embodied by both people and objects. And these social agents are agents that can cause a cultural effect in people. And I consider that cultural agent was a good way of defining the sort of evidence that I was examining. So we have people, settlements, objects, and within objects, sculptures, epigraphic inscriptions, and coin. Then the cultural contact class is also a very important one, because when examining the evidence, I saw that there were different types of cultural contact evidence. So there could be impermeable cultural contact when there is no evidence for cultural contact in the material record. So we know that there was some sort of coexistence of different groups in the area, but there is not proof for such in the material culture. And then permeable cultural contact, when we have proof in the material culture of some sort of interaction between the communities, because we have bilingual texts, or we have different influences, iconographical influences in the objects, and so on. Then the cultural contact trait is one of the main classes in the ontology, because this is the one that helps me identify cultural interaction in an object. So cultural trait is defined in COCO as the characteristics of human action that are acquired and transmitted by any kind of communication in situations of cultural contact. So in this, if we can give an example of, in this case, a cultural trait could be the laying of a coin or the iconography of a sculpture. And so all those cultural traits are typified in COCO, and we can look for them by a query, by a simple query. And once that those objects that share cultural traits which have different cultural influences, like for example, if the object has a legend written in Latin, and then it has also iconography which is identified with indigenous communities, then the ontology considers that object as a product of cultural contact, or an object that can be a proof of cultural contact. Also cultural identity, which includes all the classes that compose the cultural identity of an individual or a group, like ethnic identity, religious identity, and other cultural contact features, like the context in which the situation of cultural contact occurs, in conquest, trade, and so on. The properties are the Gabi explained it very well, is how we can connect the classes between them, or the classes with the entity. So how we can connect the object, the basic object, with the class that defines it. I'm not gonna go deeper into this because it's just these different properties that are used in COCO. And finally, I wanted to talk a little bit about the inference rules. So the inference rules are quite important in COCO because, as we said, COCO has been designed to identify cultural contacts. And so cultural contact cannot be identified directly in the evidence, but it can be inferenced using these sort of rules. And so through the inference rules, the ontology can detect if any object has cultural traits of different cultural influences. And then when that happens, the ontology considers the object as a cultural contact object. And so in this case, we can see how the statue A is model. It has a person, that person wears a toga, that toga is identified as clothing, and that sort of clothing that is here typified is considered or is associated with a cultural identity Roman. So we are with these sort of rules. Is how I configure the ontology to understand any object that has a toga in this context as having the cultural influence Roman. So if that sort of object had a toga and had also some sort of indigenous influence or Punic or Greek or other sort of influence, the ontology will identify it as I said, as an object, as evidence for cultural contact. And with this, I think I'm done for now.
Thank you, Paula. Going back to Matteo again, I would just like to point out that we're a little bit behind with time. So if you can be aware of this in your last presentations, thanks.
Sure. So we move now from the objects that Paula presented more to text. And in particular, I will present a use case on using linked open data to publish a knowledge base that helps a specific natural language processing task. So what I worked on for a while in the past was the problem of how to extract canonical references from publications. So what you see here in these slides, in the red boxes, are examples of citations of the Argonautica by Apollonius Rhodius. They are cited in publications. I'm sure you have seen it in other contexts. Traditionally, in classics, all these passages are collected in an index locorum, which you find at the end of the publication. So I was trying to replicate in a semi-automatic way this process of creating an index of citations by automatically extracting these references from text. And then, for example, creating an index and also do other types of applications. So my specific use cases is related to a project that focuses on the automatic extraction of canonical references. And the project is called Cited Loci. So the thing I was focusing on is how to, once you extract a reference, so in the previous slide, you have already pre-identified the references. Once you have your software having extracted them, you still need to disambiguate them. And by disambiguating them, I mean to assign to each reference a unique URI, a unique identifier that says this is the work being cited in this reference. So if you take the example in this slide, we need to pick the right work from our database, from our knowledge base, to link it to this reference. So in this case, we want to link the reference to the URI for Virgil's Aeneid and not to, for example, the Vita Vergili by Donatus. So that's really the task where the knowledge base helped a lot. And in fact, the knowledge base was really born to support this citation mining task. It's a pretty simple knowledge base. That's why I'm also not focusing on the modeling or on the ontology modeling side as Paula did. So it's not very complicated. It contains basically names of authors, titles of their works, and then abbreviations of author names and abbreviations of author titles. And that's pretty much it. But the purpose of this knowledge base was to support the citation mining task. So when you are connecting a reference to the corresponding record in a knowledge base, then you need, especially if you're dealing with a multilingual context, with multilingual text, then you need a lot of lexical information, linguistic information about, for example, the different variants of the names of authors or the different variants of the titles of the works in multiple languages with the abbreviations and so on. And this is all what is contained in the Hucit. So this is just to give a bit the bigger picture, how the knowledge base fits into a broader pipeline to extract these citations. So you go from the full text with a plain text, you try to identify the references. Then you have a citation matcher, which is basically trying to match each reference against the corresponding record in the knowledge base. and then the citation parser doing some normalization on the scope of the reference. This knowledge base can be used to support the citation mining, but it can also support the human annotations. And something that we have done quite a lot in the recent past is to having human annotators to correct the output of the automatic extraction of these references. So what you see here in these slides is a screenshot from an annotation environment called Inception that supports databases, knowledge bases that expose SPARQL as an API. And I was able to connect my knowledge base, which also has a SPARQL endpoint, on this tool. And this, what allows you to do is to basically feed the tool, the annotation environment, with annotations already done by a software, and then the users can go and correct the wrongly assigned links. And how you see here in the bottom right, there is a URI from a knowledge base showing up. So basically, the user goes on the reference to the N8 on the work URI menu and is able to search full text on the content of the knowledge base. So that also gives you an idea not only how, in abstract, we can publish this data as linked open data, but also, as Gabi was saying, how we can use it in our own projects. So that's one application. A bit more about the content of what's inside the knowledge base. As I said, there are authors and works. And linked open data, it's used to enrich and bridge together different sources. So we have VIAF that we mentioned already, which contain name variants for Virgil, aggregated by hundreds of library catalogs. In Wikidata, you have lots of information, links to Wikipedia pages, names of authors and works in different languages, rich descriptions. From the Perseus catalog, we have all the bibliographic information and links to online editions and translations. And in CWKB, which is the classical word knowledge base, then you have other name variants for authors and works, and also links to other not open access digital libraries that Perseus doesn't link to. So you have 4 complementary pieces of information that before Hucite, they were not connected. With Hucite, I'm trying to bridge these things together. So I have, for each author and work, links to all 4 of them. Actually, for Wikidata, the coverage, Wikidata and VIAF, the coverage is for the moment not that high. It's about 5–10% of the total, but I'm working on the reconciliation of my knowledge base to Wikidata. So that's how a bit linked open data is leveraged in the context of Hucite. A critical aspect in implementing this knowledge base was the fact that I need to use it not only to publish the data, but I want to use this knowledge base in my software, which is written in Python, that extracts the citations. And this means there needs to be kind of an easy to use programming API to the knowledge base. So I use a solution that provides you not only the SPARQL API and a web frontend for the knowledge base, but also allows you to create relatively easy a Python API that allows you, for example, here you see in this snippet, a typical session where you interact with this knowledge base as you would interact with classes and objects in Python. So you can search for a given author by string, or get all the authors, all the works, and do some counts on the knowledge base. And this was achieved by having all the information in a SPARQL endpoint and using SPARQL as an API, both to build like a web frontend to make these URIs dereferentiable, and at the same time also using SPARQL to create this Python API that allows you to use this knowledge base in normal Python programs. And at this point, I should also have a caveat saying that if you actually try these URIs to look them up on the browser, they're not working right now because I'm migrating the triple store in a new place, but there will be the web front end will be working soon again. And now I leave it to the Sparkle exercise.
Thank you, Matteo. I'm moving to Paula. Shall I share your screen?
Yes, please. Okay, and I'm gonna talk now about the practical exercise about Sparkle. So I am planning to speak a little bit about the concept of Sparkle, showing some queries, the taxonomy of the queries, and then I will explain quickly the exercise. But please feel free to email me if you have any questions. I think my email will be provided at some point, so I'm totally available about this. So to start, Sparkle stands for Sparkle Protocol and RDF Query Language. Sparkle is in the same way that SQL works for relational databases. Sparkle is the query language for RDF data, so for linked open data. At the beginning, it can be a bit overwhelming or seem to be difficult if you don't know SQL, but from my own experience, if you get familiarized with the data, with the RDF, it should be easier to understand and to use Sparkle. Sparkle allows the user to ask questions to the data set, as we have said, and Sparkle queries this, search the dataset for the specific subset of data that meets the conditions that we are establishing in the query. The anatomy of Sparkle queries is normally constituted by several sections, which require a specific order that we are going to look at in a bit. So as I said, you need to formulate the graph pattern in the query. So for example, both examples are, I took them from my research. In the first case, we are looking for a settlement that according to the Pleiades vocabularies, has a name, and that name is Osuna. So we are querying the dataset for a settlement that has name Osuna. And in the second graph pattern, as you can see, for example, we are interested in any inscription that has been found at, or that somewhere that has been found somewhere in Baetica. So this could be two graph patterns that we could define in the query. So now, how do the structure works? I will show a query in a minute, but just to make this clear, normally the queries are formed by first, the list of namespace definitions, which can be the prefixes. If you want to, this is optional, but it's preferable to make it more readable. Then the query form with different variables: select, construct, ask, and describe. We are going to use select today, but if you are more interested, you can explore the others. Then the query patterns, with where, start by where, and then different subqueries, expressions, and so on we want, and also filters. And finally, some solution modifiers. We can order the results in ascendant or descendant order. We can limit the number of results if we think that our query is going to provide many different results and we just want to get a sample of the result, a sample of the data, and the offset. So this is an example of a query that I run in my own triplet store using the Cuckoo ontology, as you can see. So at first I am defining the prefix. I am declaring the URI of the ontology that stands behind this prefix Cuckoo. And as I said, this is optional, but is recommendable. Then I am using the select, and I am looking for any settlement, as you can see here, any settlement that, well, I'm looking for this variable that from this is not necessary. This is just a selection of the graph to be queried. As you can see, I'm saying make this query for the data that comes from this graph, because I have many different graphs in my data set, but this is not necessary if you only have one graph, one big graph. And then I'm saying in the case or where that thing that I am asking for has type, this A is, it means has type in Sparkle, is a convention, and then a cuckoo settlement. So anything that is considered a settlement according to cuckoo. And finally, I am setting a limit with a modifier, with the limit modifier up to 100 results, because I know I have many settlements in my dataset and I only wanted to get the first 100. And so next, I have written some examples to query the EDH datasets. One part of the exercise will be to go into EDH, and I have prepared here the exploration of EDH to make it easier. So you just have to go into the data sets and, for example, pick a different inscription from 2 different provinces. I'm interested in Baetica and in Hispania, so I will go into Baetica, and I have selected here. I have it here just to avoid the loading time. So these are this is an example of one inscription that is found in Baetica, that is in EDH. And if you can see, this is the detailed view of the inscription with all the metadata and the different links to Pleiades and so on. And then if we want, we can download, or we can get the RDF from this link here. So if we clicked here, this would be the next view that we would get. We would get the URI will provide the RDF for that resource, for that identifier. And so here we can see that we have the subject here, this inscription, and then...
Could you zoom in a little bit, please, Paula?
Sorry?
Could you zoom in a little bit, make it larger, easier to read?
Now?
Perfect, thank you.
So one of the steps of the exercise would be for you to get a bit more information about this, like to explore this a little bit further, see if you can understand the different prefix. Where does this DC come from? This epi come from? This NMO, what ontology does this refer to? As you can see, we can see that this is the inscription that we are looking at, that is considered type inscription by the EPI ontology, and we get some metadata here about the publisher of this inscription in EDH and the contributor, and then we have more information. We can see that that inscription has a start date 24 and end date 25 CE, 24 and 25 CE. And then we can see more information about the max height, the width, the depth, and so on. So if we wanted to run a simple query to get any inscription that has max height, for example, 37, we would do something like this. This is the endpoint of EDH. I just went in the data section and then endpoint, and I want to do a simple query looking for any inscription, which I just call it S, but any other word would be okay. It doesn't matter. You can just S or inscription. I'm looking for any inscription where that inscription has a mass height, whatever, any other word would be okay, mass height something, and then I'm filtering for any mass height that is 37. So when I run this query, I get a list of all the inscriptions that have a mass height 37, a maximum height 37. And we could keep exploring it with other sorts of queries. We could even change this to, instead of mass height, maybe we want to look for any max depth, for example. I don't know if there would be any available, but there could be. Let's see if we can get. And again, we get a list of all descriptions that have a mass depth 37, the one we established. This is just a random number. If you are interested in anything in particular, you can change it. Then in the second query, all these queries we have put them in the wiki, and you can access them and copy them into the endpoint to keep exploring it. And this one, as you can see, is looking for an inscription. Here I called it inscription to make it more readable. So any inscription that inscription is considered, it has a person according to the EPI ontology. Any inscription that has a person P. And I'm gonna set the period here just in case. And as you can see, we got a list of all the inscriptions that have a person. If I was looking for the inscription, if I was looking for the inscription and the URI for that person, I can just provide that here in the graph, in the query variables, and get it here. We have the inscription here, inscription, the list of the URIs for the inscriptions, and the list of URIs for the person. And what I did now is, if we want to explore further one of these persons, one of these identifier for people that has the EDH dataset, we can just look for more information about that person. So here we have set as the subject of our graph pattern an identifier of a person, and then we are looking for all the predicates and objects related to that person. So if we run a query to get more information about that person, we can see how this is a person, that URI we queried for is a person that has a name, Caius Braetius, which is in Latin, as we can see here, and it has an attestation that we can dereference as well, and we can look into if we wanted. So if we wanted to make it a bit more complicated, we could expand the query, and this is a bit more complicated one, but follows exactly the same logic that the previous one we've seen. In this case, we're looking for an inscription, a person, a monument type, a start date, and an end date. So we are saying that the inscription has a person, that the inscription represents or has a type monument, and that type monument has to be statue-based, as we can see here, that that inscription has a start date, that inscription has an end date, and then we are establishing a filter, and we are saying, please make that start date higher than 0, so it has to be CE, and the end date, make it lower than 150. So if we run this, we should get the results of the inscription with the monument type, the person URI, and then the person, which is here, and the start date, which is here, and the end date. And the monument type is not given because we have established that it has to be statue-based. So it just doesn't provide that information because it's implied, because we are saying here that the type monument has to be statue-based. So just to finish, the exercise that we are proposing here is, just as I show you, go into the epigraphic database, into EDH, and look at the RDF. behind 2 or 3 inscriptions from different provinces and see how much you can understand or guess. Go then, once you have got a good knowledge about the RDF and how it works and what you can identify there, then go to the EDH Sparkle endpoint and enter the sample searchers from the presentation that we have given you and try to understand what's happening there, what they are returning. Using your sense of the RDF structure, then you can come up with new searchers, combining the example with syntax that you have learned from Sparkle to explore the data further. And for example, ask for the first 50 person names in inscriptions from the 2nd century, which would be something very similar to the last example I have shown you, but you can expand it and create the queries that you are more interested in. And finally, if you want, you can visit nomisma.org, the Triple Store, and explore their data. And using some of their sample Sparkle queries and the knowledge that you have acquired in the first few exercises, you can try to come up with some queries to explore their data a little more and see if you can understand what is going in their queries. And with this, I am done for today.
Thank you very much, everyone. That was a very, very useful introduction, a practical introduction to linked open data. And we have already overrun a little bit, so I don't want to take advantage too much of our speakers. But if you have questions for each other, or if any of the people that are watching on YouTube want to ask any questions live, please use the comments on YouTube. We will read the questions live. But if any of you wants to get started, if you are available to stay with us, just maybe five minutes longer. Some of you are muted.
Sure.
As I said, I'm happy to answer any questions, and to provide my email to the students once they have already explored the endpoints and the data sets. I'll be happy to. I know at first it can be a bit tricky, so that's totally fine.
Yeah, thanks. Yeah, no, I would say though for the exercise, which by the way that exercise is in the session page on the GitHub site for Sunoikisis, as well as in the slides. And in the session page, there are links to the epigraphic database Heidelberg, to their Sparkle endpoint, to the examples that we've given, and to Numisma, the Triple Store, and their sample Sparkle queries. So everything you need to do the exercise is linked to in there. I think the important thing for the exercise is to look at some of those examples, look at some of the examples of RDF, look at some of the examples of Sparkle, and first look at it, freak out a little bit because it's hard, it's complicated, it's lots and lots and lots of very small print, which isn't going to mean very much to start with, lots of pointy brackets, and then just poke at it a little bit, and copy and paste some of those sample queries into the Triple Store, see what comes out, think, okay, I think I know what happened there. So what happens if I change that 37 to 63?
Yeah.
Will it give you some different results, or will it break because you've changed something that you did in the wrong way? And then breaking it actually is a really good way to learn more about it. And so I'd say for the class students, the aim is to play with it, to break it, and to see what you learn, from trying this, to really sort of change things. Saying, okay, they've given us a couple of easy things to tweak. It's like change it from 37 to another number. Well, that doesn't teach us anything. So try changing something completely different. And if it doesn't work, turn up next Tuesday and ask Valeria why not.
I would like to remind Gabby that he's going to be in the class on Tuesday.
That's true. You could ask me too. Why not? Yeah. And then if I think the point at which anybody decides they want to use RDF or linked data in some form in their assessed work, that's the point at which we might, when things start to get really hard, ask Paula for help, because she is the sparkle queen in this one. And if anyone wants to do, citation resolution of any kind, then we'll have to ask Matteo, who's the citation resolution queen.
But no sparkle.
No, Paula is the sparkly one. Yes, linked open data, in my experience, is something that looks very difficult at the beginning, because it sounds a little bit abstract, at least in the way that was presented to me. But when you start getting into it, it is possibly the most useful technology that I've ever learned. And when you get it, then it looks almost obvious, but it is, a little bit of a step to get to be simple. It has to be hard before it becomes simple.
Yeah.
So I have a question for both Paula and Matteo, and possibly for Valeria too, which is that, so we've seen RDF, we've seen Sparkle, we've seen examples, and both of the case studies involved, very smart, very technical people writing code, writing script to make this stuff work. Is linked open data and RDF and Sparkle something that can only be useful to a programmer, to someone who is a hardcore coder? In what sense, in what form does it ever become useful to the general public, or to a non-technical user, shall we say?
Who wants to answer this?
I can go. But,
okay,
I don't know
follow.
Okay, I don't know what you think, but I would say it's primarily meant for not for developers or programmers, but at least to be consumed by people who can code. Of course, if you have interfaces that make use of it, then it's very useful to explore things. But then you need to program a front end to some linked open data. So I think immediately it's probably the target audience are developers or anyone who can code to make use of it. But then you can build things that are used and useful to anyone. So that would be my attempt to an answer.
My answer, let's say, piggybacks on Matteo's and focuses on this intermediate step, if you want, these intermediate tools that are, APIs, interfaces that make linked open data visible, browsable, messable by anyone. Things like Periplay, or things like, what Research Space wanted to do. So things that make the linked open data that someone, more technologically minded produce useful to anyone. I think that is where we should go, because linked open data should have a much wider audience than it has now. I mean, I think that is the point. Otherwise, it's just for a small group of researchers, and it would be such a wasted opportunity. So we should think of, either a simpler language than Sparkle, or interfaces, or I don't know, teach everyone how to use and produce linked open data starting from primary school. I don't know.
For me, the most valuable power of linked data, if you want to look at it like that, is how it makes research reusable. In my case, the possibility to consume data that was already there in EDH, in MISMA, and in many other data sets is what made the point. Like, why would I need to create a new data set of epigraphic descriptions from Bioetica if that is already there? And thanks to linked open data, it's easy to consume, and you don't need to be an expert. As long as you can go into the data set and get download of it and generate a CSV, it's easy to query and easy to look at it and reuse it. And for me, that's fundamental to make research reusable so that it survives and persists.
Yeah, I mean, linked open data for everyone was Pelagio's dream, basically. So I think we did achieve something in that direction, but there is still work to do.
Can I ask a supplementary question then? Can you give an example, or is there a sense in which we are all using linked open data without realizing it? In some cases, is it invisible anywhere that we might know?
Well, I think the linked data, not necessarily open, are pretty much ubiquitous in a lot of technology that we use, a lot of commercial technology that we use. The linked open data, that I couldn't think of immediately of a non-obvious example, or a non-academic example of it.
Mm.
Okay, but linked data then, where the technology is exactly the same, just it isn't open. Is that fair to say? That you'd see everywhere. So when you search in Amazon, there's linked data in the background. When you do Google search, there's linked data in the background. Facebook has linked data everywhere.
Every service that tells you people that bought this also looked at this.
Mm-hmm.
People, services that say, people that like this movie, also like these shoes. They are usually, I think, semantic technologies that are very close to linked data. A lot of things that are geo-based also rely on linked data.
Right. So Google Maps must have it everywhere. Yeah.
Anytime we refer to another website in our research to kind of make a point that what we are saying is already said somewhere, that's linked open data in its more basic form, because we are using the URI of that website to make a reference to our point.
I think at the same time, it's also inevitable a bit that it becomes invisible, because linked open data, it's consumed and then you can build other things on it, but you don't even necessarily state anywhere that it's actually built using behind the scenes linked open data. So we might actually be using already things that we don't realize are powered by some use of linked open data, I think. Because
is it open then if it's invisible?
Invisible in the sense that it's behind the scenes. It's used behind the scenes, processed to enrich your experience, but you don't realize. And I think, if it's using open data that are linked, it's still linked open data, even if it's not stated that it's being used.
So you could get to it, just you don't need to.
Yeah, or you could be using something that is powered by linked open data and you don't realize it.
Yeah.
Well,
good. Okay, we are getting really late now, and I hope that all the people that follow this class are now ready to become partisan of linked open data. And we can thank our speakers for today and see you next week. Bye.
Thank you. Bye.
Bye.
Bye.